You think you already know what an atom looks like. You've seen the diagrams countless times. A tiny nucleus sitting at the center like a solid. Electrons looping around it like planets circling a sun. Neat. Orderly. Easy to sketch. That image lives in every school textbook. Science museums hang giant versions of it from their ceilings. Little spheres connected by thin wires, spinning in perfect, predictable circles. But here's the uncomfortable truth. That picture is wrong. Not slightly inaccurate. Not good enough for a basic explanation wrong. It's completely, deeply, fundamentally wrong. Wrong in a way that should make you pause and rethink almost everything you were taught about how matter works. An atom is not a tiny solar system. Electrons are not miniature planets. And if you try to understand what's actually happening inside an atom using that picture, you'll hit a wall fast. You'll get confused. You'll start asking questions that seem impossible to answer. Not because physics is broken, but because those questions are built on a false idea from the very start. So let's wipe the slate clean. Let's talk about what's really inside an atom. Fair warning, you're probably not going to enjoy this. Because what's actually there is so strange, so far removed from everyday intuition, that your brain will resist it at every step. We'll begin with the simplest atom of all, hydrogen. Just one proton, just one electron. That's it. This is the atom everyone uses to explain the basics, because it's supposed to be simple. You imagine a proton parked at the center, a tiny ball about 10 superscript 1 meters across. Somewhere far away, maybe 10 superscript 1 meters out, the electron circles around it like a satellite. So the obvious question is, where exactly is the electron? Your instinct says, it's right there, on the left side of the atom, moving along its orbit. That instinct is wrong. The electron is not over there. The electron doesn't have a fixed position. Not because our instruments aren't precise enough. Not because we simply haven't looked closely enough. The electron itself doesn't have a definite position until you measure it. This isn't philosophy. It isn't some weird interpretation. It's what the math demands. It's what experiments keep confirming again and again. The electron exists in a state we call superposition. It isn't here or there. It's here and there at the same time, simultaneously in multiple locations. Some people imagine this as a cloud surrounding the nucleus, a hazy mist of probability. You might think, okay, so the electron is smeared out, like butter spread over toast, thin and diffuse. No, that's still wrong. The electron is a point particle when you measure it. Before you measure it, it has no position at all. What is spread out is not the electron itself, but the probability of where it might be found. This is described by a mathematical object called the wave function. It tells you where you are most likely to detect the electron. In some regions, the wave function is large, high probability. In other regions, it's tiny, low probability. In some regions, it's zero. You will never find the electron there. Here's the part that really twists your intuition. Before you look, the electron isn't secretly sitting in one of the high probability spots. It's not hiding. It simply doesn't have a location. The wave function is the electron. That's all there is. Now, let's get to orbits, the part where the solar system analogy completely collapses. You might picture the electron swooping around the nucleus in a neat circular track, round and round, like a racetrack. Maybe fast, maybe slow. Surely it's moving somewhere, right? Wrong. Let's take the first problem. If an electron were actually orbiting the nucleus like a tiny planet, it would constantly be accelerating. Anything moving in a circle, even at a steady speed, is accelerating because its direction keeps changing. And here's the kicker. Accelerating charged particles radiate energy. They give off light. That's basic electromagnetism. We can measure it. It happens. So, if electrons really orbited the nucleus, they would be losing energy all the time, radiating it away as light. As they lost energy, their orbits would shrink. They'd spiral inward, faster and faster, until, crash, they hit the proton. The atom would collapse. How fast would this happen? Do the math. About 10 superscript 1 seconds. 1/10,000,000th of a second. Every atom in the universe would vanish instantly. Obviously, that doesn't happen. Atoms are stable. They don't collapse. So electrons can't be orbiting. Okay, maybe you think, fine. Maybe the electron isn't orbiting. Maybe it's just sitting there, motionless, held in place by the electric pull of the nucleus. Also wrong. Because if it were truly sitting still, we would know both its position and its momentum exactly. Position, right there. Momentum, 0. Quantum mechanics forbids this. You cannot know both exactly at the same time. This is the Heisenberg uncertainty principle. It's not about faulty instruments or sloppy measurements. It's a fundamental law of nature. Pin down the electron's position, and its momentum becomes uncertain. Pin down its momentum, and its position becomes uncertain. You cannot have both. So, the electron is neither orbiting nor sitting perfectly still. The real question is, what is it doing? It's not doing anything. It simply exists. As a wave function, a mathematical description of probabilities. And this wave function has certain allowed shapes and energies. These shapes are what we call orbitals. But an orbital is not a path. It's not a trajectory or a racetrack for the electron to follow. It's a region of space where the electron is likely to be found, as described by the wave function. The simplest orbital, the ground state of hydrogen, is spherically symmetric. The probability cloud is densest right at the nucleus and gradually fades as you move outward. No orbit, no path, just a fuzzy cloud of might be here. Higher energy orbitals take on stranger forms. Some resemble dumbbells. Some look like donuts. Some have multiple lobes. These shapes aren't physical objects. They're maps of probability, regions where the electron is more or less likely to be detected if you look. And here's the part that really defies intuition. The electron doesn't slide smoothly from one orbital to another. It doesn't glide gradually from the ground state to an excited state. It jumps instantly. This is what we call a quantum leap. One moment, the electron's wave function is in the shape of the lower orbital. The next moment, it has the shape of a higher orbital. There's no in-between, no smooth transition. It doesn't travel through the space separating the orbitals. It simply appears there. How does this happen? We don't know. The math describes it. Experiments confirm it. But there's no mechanism, no classical explanation for how it moves from here to there without passing through the middle. And now, the truly mind-bending question. What is the electron really? So what about these electrons? You might imagine them orbiting the nucleus. No, stop. Not orbiting. They exist simultaneously as wave functions, spread out around the nucleus. Here's the mind-bender. All electrons are identical. Perfectly, fundamentally identical. There's no way to distinguish one from another. Not because they look similar, not because their properties match. They are the same. Electron number 1 and electron number 2 aren't just similar particles. They're literally the same entity appearing in different places. And this has profound consequences. Swap 2 electrons, and the wave function of the entire system changes sign. It picks up a negative factor. This is not a minor detail. This is fundamental physics. It's called the Pauli exclusion principle, and it is the reason matter is solid. It's why you don't fall through the floor. It's why atoms have structure. It's why chemistry works. It's why life exists. No two electrons can occupy the same quantum state. If one electron is in a particular orbital with a particular spin, no other electron can take that same state. They have to stack up, filling different orbitals, creating the patterns we recognize in the periodic table. Without this rule, all electrons would collapse into the lowest energy state. Every atom would be chemically identical. There would be no diversity, no molecules, no chemistry, no you. But why does swapping identical particles flip the wave function sign? We don't know. It's simply a rule of nature we discovered. The math works. The experiments confirm it. But there's no deeper explanation. It's just how the universe behaves. Now, let's turn our attention to the nucleus, which most people think is simple. A cluster of protons and neutrons, tightly packed together, little solid balls stuck in place. Wrong. Protons and neutrons are not fundamental. They're made of quarks, 3 quarks each. Up quarks, down quarks, held together by the strong nuclear force, mediated by particles called gluons. And here's the part that will twist your intuition. The quarks aren't sitting still inside the proton. They're quantum fields, fluctuating, interacting, constantly exchanging gluons. A proton doesn't hold 3 quarks like a bag holds marbles. It's a bound state of quark fields, a stable, oscillating pattern. And the truly mind-blowing part, most of the proton's mass doesn't come from the quarks themselves. Quarks are nearly massless. The majority of the mass comes from the energy of the gluon field holding the quarks together. Energy equals mass. So when you ask, What's inside a proton? The answer is energy. Bound energy in a stable configuration, not stuff, not particles, just energy arranged in a persistent pattern. And the protons and neutrons inside the nucleus? They're held together by the residual strong force. They're not touching, not glued together. They're trapped in a potential well created by the exchange of particles called pions. And here's the kicker. Pions themselves are made of quarks. It's quantum fields all the way down. So let's take a step back and ask the question again. What's really inside an atom? Not particles, not little balls, not neat orbits, not stuff. What's inside an atom is fields. Quantum fields. The electron field, the quark field, the gluon field, the electromagnetic field. These fields fill all of space. They're everywhere. Always. When we say there's an electron in an atom, what we really mean is that the electron field has an excitation localized near the nucleus. The atom is not a thing. It's a pattern. A stable configuration of field excitations, held together by forces that themselves are carried by other field excitations. There are no solid objects at the bottom. No stuff. There are only fields, mathematical objects that assign numbers to every point in space and time. Numbers that evolve according to differential equations. Numbers that sometimes produce localized excitations we call particles. I know what you're thinking. You want something real at the bottom. Something solid. Something you can point to and say, that's what it's made of. There isn't. There's only math, equations, symmetries, conservation laws. And somehow, miraculously, that math produces the appearance of solid objects. Tables, chairs, your body. All of it is patterns and quantum fields, held together by forces, stabilized by exclusion principles, flickering in and out of existence trillions of times per second. Here's something else that will twist your intuition. You've probably heard that atoms are mostly empty space. That's not quite right. Empty space doesn't mean nothing. Quantum fields are still there. Virtual particles are popping in and out of existence. The vacuum is seething with activity. And the electron's wave function? It fills the entire atomic volume. The electron exists in the sense that its probability amplitude is non-zero throughout the atom. When you push on a table, you're not feeling particles colliding. You're feeling electromagnetic repulsion between electron clouds. You're feeling field configurations resisting overlap. You're feeling the Pauli exclusion principle, preventing electrons from occupying the same state. It feels solid because the forces are strong. But there's no actual contact, no touching, just fields pushing against fields. Now let's talk about size, because this is where your intuition really fails. The nucleus is about 100,000 times smaller than the atom. If you scaled the nucleus up to the size of a marble, the atom itself would be the size of a football stadium. But here's the kicker. The electron itself, as far as we can tell, has no size. It's a point particle. Every experiment ever performed comes back with a result consistent with zero. So, somehow, you have a point particle with no size occupying a volume about 10 superscript 1 meters across. Does that make sense? No, of course not. But that's what the experiments tell us. Nature doesn't care whether it makes sense to you. Now, let's make things even stranger. Spin. Electrons have a property called spin, which behaves mathematically like angular momentum. It acts as if the electron is rotating. But the electron is not spinning. It can't spin because it's a point particle. A point has no extent, nothing to rotate. And yet, the electron has angular momentum. Intrinsic angular momentum. Momentum that doesn't come from motion. It's just a property the electron has, like charge or mass. We call it spin because it behaves like angular momentum mathematically, but it is not actual rotation. This spin is quantized. Spin 1/2. Measure it along any axis, and you always get one of two results, up or down. Never anything in between. And here's the mind-bending part. Before you measure it, the spin doesn't have a definite direction. It exists in superposition. The moment you measure it along one axis, it becomes uncertain along perpendicular axis. Why does it behave this way? We don't know. We don't know why. It's just how spin works. Nothing in your everyday experience behaves this way. And energy? That's even stranger. Energy levels in an atom are quantized. The electron can only have specific energies, not just any value it wants. Discrete, fixed, precise energies. Why? Because the wave function has to fit around the nucleus. Think of it like a vibrating string. A string can only vibrate at certain frequencies, the fundamental and its harmonics. Same with an electron's wave function. Only certain wavelengths are allowed. And since energy is linked to wavelength, only certain energies are allowed. When the electron jumps from one state to another, it emits, or absorbs, a photon with exactly the energy difference between the two levels. This is why atoms emit light at specific wavelengths. Why hydrogen has its distinct red line, its blue line, and so on. Each line corresponds to a specific quantum jump between energy levels. We can measure these wavelengths to extraordinary precision and predict them using quantum mechanics with the same mind-blowing accuracy, 10, 12, even 14 decimal places. The theory works perfectly. But why are energy levels quantized? The math tells us. The experiments confirm it. But there's no deeper reason. Now, let's talk about what happens when you try to look inside an atom. You can't use visible light. Its wavelength is bigger than the atom itself. You need something with a shorter wavelength, higher energy. But here's the problem. The moment you use high-energy probes to look at the electron, you disturb it. You knock it out of its state. You change what you're trying to measure. This isn't a technical limitation. It's fundamental. To see something that small, you need short wavelength light. Short wavelength means high energy. High energy means large disturbance. You can't avoid it. The very act of measurement changes the system. At the quantum level, there is no such thing as a passive observation. This is why we cannot say where the electron is before we measure it. Not because it's hiding somewhere, but because the property of having a definite location simply doesn't exist until we perform a measurement that brings that property into being. Before measurement, the electron is described by a wave function, a superposition of possibilities. After measurement, the electron is found in a definite state, one of those possibilities. The measurement doesn't reveal a pre-existing reality. It creates a definite reality from a fuzzy, probabilistic one. So what is really inside an atom? Not little balls, not orbits, not stuff, not even particles as you imagine them. Inside an atom is a mathematical structure, a wave function, a solution to the Schrödinger equation, a pattern of probability amplitudes that tells you what you'll find if you look, but doesn't describe a definite reality when you're not looking. The atom is a quantum system, and quantum systems don't behave like anything in our everyday experience. They exist in superpositions. They have properties that are fundamentally uncertain. They defy visualization. You cannot picture what's inside an atom because there is nothing to picture. The wave function is not a physical wave in space. It's a function in an abstract mathematical space called Hilbert space. It's a list of complex numbers encoding probabilities. It's information, not substance. And yet, from this abstract mathematical structure, the entire physical world emerges. Chemistry, biology, consciousness, everything we see, touch, and experience arises from the patterns of quantum fields and the rules of probability. All of it is built from patterns in quantum fields, governed by equations that defy intuition, yet work with astonishing precision. This is what's truly inside an atom. Not particles, not solid stuff, but math. Pure, abstract, elegant, and deeply incomprehensible. And if that answer leaves you unsatisfied, if you still want there to be something solid at the bottom of reality, something tangible you can point to and say, this is what everything is made of, I'm sorry, the universe doesn't care what you want. It simply is. And what it is far stranger than anything you were ever taught to imagine.